All right, so nice to meet you, everyone.
Huang from Harvard presenting the talk on advancing data aspect AI.
Thank you. So, yeah, so nice to meet you all. Today, I'm very pleased to give you this seminar talk about advancing data aspect AI from efficient data annotation to high quality data creation. So my name is Huang, and I'm currently at Harvard as a postdoc fellow. And before joining Harvard, I was in Nanyang Technological University as a postdoc, and I was a research scientist at Baidu Research. And I was visiting Carnegie Mellon in 2018 for a whole year. And before that, I graduated my PhD from Zhejiang University in 2019. So my research areas are generally computer vision, deep learning, and generative AI. So my research vision is to make AI both understand and create visual and multimedia contents. So under this vision, I have several specific topics, including image generation, image understanding, multimodal understanding, and effort-efficient learning. So in this talk, I will only cover the yellow parts. I will start from the effort-efficient learning topics like active learning and semi-supervised learning. Then I will move to image generation topics like neural style transfer. So since 2012, we have witnessed a big success of deep learning. We have image recognition systems that can recognize the fine-grained objects from the images. And we can also transfer the speech to the text using the speech recognition systems. And in more recent years, we have more fantastic applications of deep learning, like the creative generation powered by Stable Diffusion or DALL-E model. So they can generate highly realistic images from the texts. And also we have the AlphaFold model that can discover the protein structures to help the medical scientists to discover drugs. But the factor behind the big success of deep learning is the large scale data. So for example, for image recognition, the ImageNet dataset has more than 1.2 million images with fine-grained object category annotations. And for speech recognition, the cutting-edge systems use more than 600K hours of audios with parallel text annotations for training the models. And also for creative generation, the DALL-E2 model uses more than 400 million image text pairs to train the model. And also for drug discovery, AlphaFold 2 model trains on 170K protein structures. And actually these structures are almost all of the existing known structures discovered by humans in the past decades. So deep learning is very data hungry. Here I illustrate the performance versus the amount of data. So when the amount of data is relatively small, then the traditional learning algorithms will outperform deep learning. But when the amount of data gets to a scale, then deep learning will significantly outperform the traditional learning algorithms. So deep learning requires a lot of annotated data, but the annotation is often very expensive. For example, in this figure, if we want to annotate every object in this image, then we may take maybe even 1 hour or much more time to annotate every object, including the boundaries and the semantic categories. So this is very this will cost a lot of human efforts. And we have a problem that what data should we annotate to maximize the model, the machine learning model performance, if we only have a limited human resource to annotate the data. We cannot annotate the full unlabeled data. We can only annotate a small portion of them. So this problem is studied by active learning. So in active learning, we have a human annotator, and in each cycle, we select a small portion of data from the unlabeled data pool. Then we ask the human annotator to annotate the samples. Then we select, we send the samples to the labeled training set. Then we train a machine learning model based on the training set. And in every cycle, we repeat this process. Then finally, we get a good machine learning model. So you can see that the core of active learning is to design a strategy to select the samples from the unlabeled pool. So in the past decades, there have been a lot of active learning strategies proposed by researchers. For example, based on the data diversity and based on the uncertainty of the posterior probabilities, and also some hybrid methods to fuse them. But in the deep learning area, so we are curious, do we have a provable active learning method specially designed for the deep neural networks? And our answer is yes, we can look into the empirical loss of the unlabeled data. So in general, here is a deep neural network, and we input the data X to the neural network. Then we have the prediction, and we may have a ground truth label Y here. So we compute the empirical loss between the two terms, the prediction term and the target term. So if an empirical loss is larger, it probably denotes that the sample is more informative to the model compared to the samples with lower empirical loss. So we want to select those samples with more information for annotation in active learning framework. But
so you
yeah.
The constant copiers, what do you mean by empirical?
It can be anything. Here it can be anything. So but in active learning, here is a challenging problem. That is, we don't have the ground truth label because we are going to select samples from the unlabeled pool. So we don't have the ground truth labels for those samples. So the problem is, how can we estimate the unlabeled sample loss? So in my recent work, we propose a loss proxy called temporal output discrepancy. And it is very simple, and it can estimate the unlabeled sample loss. So you can, in the right figure, you can see that we just input the data X to the previous model and the current model. Then we compute the distance between the outputs of the two models. Then the distance is the TOD distance. And the motivation behind this method is if a sample has a larger empirical loss, then it would cause larger output change. And this is more informative to the model compared to the samples with lower, smaller output change. But this is just one heuristic motivation. And we still want some theoretical support for this method. So in this work, we further provide some upper bounds for the methods. Here you can see that we first provide the upper bound for the one-step TOD. That is the TOD from time step t to time step t+1. So here the eta is the learning rate, L is the empirical loss, and F is the neural network. So so naturally we have the corollary for the t-step TOD. It is accumulated from time step lower t to time step t plus upper t. So let's take a second to look at this inequality. Here, t and t plus upper t, they are two time steps of model gradient descent. And eta is the learning rate, c is a constant, L is the empirical loss. So it means that if we fix the learning rate eta and we fixed t and t plus upper t, then actually TOD lower bounds the cumulative sample loss from time step t to time step t plus upper t. So this is a very good property that it means that TOD actually theoretically approximates the unlabeled sample loss in this way. So with this property, we can design a very efficient, very simple active learning method. We just input unlabeled data to the task model of current cycle and task model of previous cycle. We compute the TOD between the two models. Then we select those samples with larger TOD values for annotation because those samples would probably have larger empirical loss. So this is very simple, but it works well for different image tasks like image classification data sets here, CIFAR10, SVision, Caltech 101, STO10. They are different image classification data sets. And here the blue lines denote the performance of TOD, and TOD works well, works better than the previous state-of-the-art different data sets, and also on most of the active learning cycles. And also TOD is very efficient. Compared to the previous work, TOD takes less time for selecting those samples. And one big advantage of TOD is it doesn't rely on an extra model. Because some previous works like VAAL and LL4AL, they use an extra model to predict the amount of information of each sample. But TOD only relies on the task model of current cycle and the task model of previous cycle. So it's very efficient. It doesn't rely on extra model.
So you
Yeah.
You are reclassifying the raw data set and calculating the distances with previous and after one.
You mean for active learning setting or our method?
Your
In our method, we just compute the TOD for all the unlabeled samples. It's very efficient. We just do one forward process, very efficient. So yeah, calculate the.
So you get a prediction from your model, which is already trained for the label data, right?
Yeah.
So now your unlabeled data, you get a prediction.
Yes.
So that's the probability that's it's the vector. And then you compare that with the previous one. Previous one on what? On the.
They are in different gradient descent steps, SGD steps.
But the question is that for that particular sample, you get prediction.
Yes.
Now you compare that with what? The subtraction is done. So I vector, I know that, So you are subtracting from which one? What's the other vector? You say there's difference, right?
Yeah, so we have we compute the TOD for each sample, right?
Yeah, but this TOD is computed out. You have so you're saying a mini train and you have now one sample is unlabeled, you get prediction, yes?
Yeah.
You get a vector.
Yeah.
And that's one vector.
Yes.
And you subtract that from what?
Subtract from the model, the previous model. So we have two models, the current model and the previous model, and we do two forwarding process.
Okay, so
Then
there may be a train model, so you put a label there, a sample there, it gives you prediction, and then the previous one you don't, you just use as it is or something.
We just store the parameters of those previous models. Yeah. Yeah.
And you subtract from those.
Yeah.
You get prediction from that.
Yes.
And then that's give you idea of that whether you should.
Yes.
Label
If the the distance is larger, then it's more informative. So yeah, so since TOD can approximate the unlabeled sample loss, it can be used for more machine learning problems such as semi-supervised learning and model selection. TOD is a very basic method. So for example, for semi-supervised learning in our further work, we applied to the semi-supervised learning. We designed a very efficient unsupervised TOD loss. And it's very simple. We just input the unlabeled data to the previous model and current model. We compute the TOD distance between them. Then it's the unsupervised TOD loss. And the unsupervised loss can be jointly optimized with the task loss under the framework of semi-supervised learning. So here is some experimental results. Here we use 40% labeled data and 60% of unlabeled data in the CIFAR10 and CIFAR100 data sets. And if we apply the TOD-based semi-supervised learning methods, we got some improvements over the baseline model. The baseline model is a ResNet, is a standard ResNet. So if we apply the TOD-based active learning method to the baseline model, we also got some improvements in performance. But if we apply them, we apply both of them to the baseline model, we got larger improvements in performance. So it means that the two terms can be jointly used when we have a small portion of label data and large portion of non-label data. So we can use both semi-supervised learning and active learning to enhance the performance.
So in semi-supervised learning, you decide whether you should take that particular pseudo label based on that your metric, right?
It's not pseudo label, it's just some kinds of consistency regularization term.
But I mean, that's, the whole idea of semi-supervised learning, that you have unlabeled data.
Yes.
And you want to label it based on your whatever you know.
We don't actually want to label it. It's just kinds of regularization term here, the unsupervised TOD loss. That is to minimize the distance between the previous model and the current model outputs. That's the.
Okay, so semi-supervised learning, you have some label data, other than label.
Yes,
right?
yes.
And you want to train your network.
Yes.
So one is, you can use a pseudo level.
Yes.
Right? That you take a train model and design.
Yes.
Use those pseudo levels to train.
Yes.
So is your semi-supervised learning method is what? Is it pseudo level based or is it consistency based?
It's consistency based. It's not the pseudo label. Yeah.
Okay, so you somehow use something else. I see. Okay, good.
Yeah. So we can also apply TOD for model selection problem. Here we input the validation data to the previous model and the current model. Here we compute the TOD on the model level. That is, we average the TOD values for each sample regarding one model. Then we get the model level TOD value. Then if a model has a larger TOD value, then it means that the model would have larger empirical loss or test loss or validation loss. So we will remove them from our model pool. And also for early stop, it can also be used for early stop in the training. Like if we train multiple models at the same time, then if a model has a larger TOD value, we just stop it because it would have a larger empirical loss in the end.
So this temporal thing you are saying is the way that network is trained. Right?
Yeah.
The different iteration.
Okay. Yeah.
So you take the unlabeled in the active learning equation.
Yeah.
So you take a unlabeled data, a sample, and with that you don't update the weights. Do you update the weights with that unlabeled or not?
In model selection, we don't update. Weights. In active learning, we also don't. Only in semi-supervised learning we update weights.
So you don't update.
Yeah,
right?
yeah.
So then, what is because if you are not updating the weights, these are the same as it was before. So what's the difference?
Oh, they are in different SGD steps. So we train the model using the task loss. Here, we're using the task loss, right? So for active learning here, yeah, we train the model using the task loss, and we have different parameters at different SGD steps, right?
Yeah, but then, I mean, how do you do the SGD step if you don't know the label of that particular unlabeled data, right? Because
that's the model is trained fully supervised in active learning.
So it is trained fully supervised for the labeled data.
Yes.
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 And now you have unlabeled data.
Yes.
One sample, you run it through, and it will predict something.
Yes.
Right. So that's one vector.
Yes.
The other vector you are subtracting. Where is that other vector coming from?
Oh, that is from the previous model. So we store the parameters of previous model.
What is the previous one? What do you mean by that?
In first epoch or second epoch, there are two models.
Train it. You mean during the supervised learning?
During supervised learning.
Oh, okay.
Yes.
But which epoch?
So
That's-
there are some actually there are some application studies that the gap. Yeah.
Basically, you are using the supervised
Mm.
learning different epochs. in
Yeah.
the brain,
Yes. Yes.
right? So
Yes.
that's the
Yes.
part.
Yes. Yes.
Okay.
So you have three,
Mhm.
so you train this model with up to a certain box.
Yeah.
And then in the next step, you train an extra epoch or several.
Yes.
But with a larger supervised data set. Yes.
Yes. Yes. Yes.
So you
Yes.
keep adding to the supervised data set, so the original epochs are smaller because you have less data. Right?
Yes.
Then you
Yes.
get larger and larger.
Yes. Yes. That is active learning. Yeah. So you can see that for the experiments of model selection, here we want to select the best model from 10 candidate models. So it means that we just train the ResNet on CIFAR 100 for 10 times. They are initialized with different parameters randomly. So our method performs better than the previous model selection methods and also performs better than the training loss. So a little better than the training loss. So it means that we can better estimate the validation loss or testing loss compared to just using the training loss.
So you compare these with the standard dropout, the common one, the classical method. For the
Dropout.
ICMC dropout.
We
The standard
didn't.
method get the
We didn't compare that. Here, these methods are generally the uncertainty-based methods.
Yeah, but uncertainty you can get from MCMC dropout, right?
Yes.
So that's a very standard and active learning.
Yes. Yeah, but we didn't compare that. Sorry. Yeah. So and what we find that active learning is super effective for medical domains or biomedical domains, because in those domains, medical images would have larger noise in its annotation, and also there are severe label imbalance problems in these data sets. So in our recent work published on MIDO, that is the medical imaging with deep learning, a very good medical imaging conference. Then we design a non-learning active learning method for the medical data sets, because we find that some learning-based methods cannot perform well on these data sets because these data sets have a lot of outliers and label imbalance problems. So we design a non-learning method for it. It is called hard contrast, and it's very simple. We just augment the original images with using some data augmentation methods. Then we test if the task model can identify those samples. If it cannot identify, then we call it hard contrast. And we use this rule to achieve much better performance compared to the learning-based methods. And also for the cryo-ET data, it's a 3D tube actually. Here I show a 2D slice, and the 2D slice is a cell. It actually belongs to a 3D tube captured by the cryo-ET machine. And we also design some gradient norm-based methods to achieve better performance. So that is the first part of my talk, that is efficient annotation by active learning, semi-supervised learning. And also in the second part, I want to discuss the data creation applications. So nowadays, generative models become really powerful, and it can create highly realistic contents to meet our human needs. So here is just one example that I generate this thumbnail image using the DALL-E 2 model. Using the prompt like a high-tech robot is sitting before the computer, using computer to view photos. It's very interesting, but it's reasonable, it's realistic. But there are still some artifacts in the images. If you look at it carefully, like in the keyboards, the keyboards of the laptop, are not very clear. There are some artifacts. So it means that there is still some improvement space for our researchers to further improve current models, even those large scale models. So here is another interesting news. A man in the Colorado state used the Midjourney tool to generate a highly realistic artwork to won the first prize in one fine art competition. And it's very, maybe some of you have heard of this news. And actually, in my opinion, this is one of the milestones that the creative generation came to the vision of more and more people. And in current days, we have more powerful tools like Midjourney V5 or Stable Diffusion are the variants. So this area is still moving very fast, developing very fast.
So Midjourney, which method are they using?
Uh,
They're not using Stable Diffusion.
I think it's based on Stable Diffusion.
Stable Diffusion?
Yeah, I think,
see.
yeah.
So all these methods are Stable Diffusion.
Yeah, because it's publicly available. Yeah, yeah.
Okay.
So I have, so in addition to the text to image generation problem, I have explored some other interesting image synthesis or image generation problems. For example, the conditional image generation. Here we can generate the highly realistic human images according to the pose given by users. And also there are some applications like image restoration problems, like image super resolution or image low light enhancement, that we can recover the image from the low light conditions or noisy conditions. And also there is a very standard, that is a benchmark problem called image translation. So we want to transfer one image to another domain, but still keep their spatial structures. So for example, in this work, I transfer the tiger face to the cat face, but keep their structures, spatial structures, like the positions of the eyes, nose, mouth, and also the shapes of the mouth. So it's very interesting and also useful in many practical applications. But in this work, I want to detailedly discuss the neural style transfer problem. There are two motivations. The first motivation is it's very interesting. It can generate the realistic artwork given content image and style artwork image. And another motivation is it is a bit more complicated compared to the image translation problem, because we need to both discover the information from the content image and also the style reference, like the textures or the style information from the style image. Then use a neural network to generate an artwork. So this is more complicated compared to the image translation. And neural style transfer is not a very new topic, and it has been studied for several years. And in some current commercial tools like Photoshop 2021, they have a function called neural filter. So here you just select the style image and give some conditions like the strength of the styles. Then you can have a good stylization result. But you can see that there are still some artifacts in the image, like there are artifacts above the mountains. So it means that there are still some problems in current neural style transfer methods. And in this talk, I will discuss two of them. So the first problem is the visual quality. So you can see that the generation here is good. It is aligned with the content, aligned with the style inputs, but the visual quality is not guaranteed because it's not very realistic to our human eyes. If we human look at this image, and we will immediately realize that this is not a realistic artwork. This is because the textures in the generation are not well aligned with the content image. So the visual quality is not guaranteed. So I also surveyed the methods from 2016 to 2022. And there are 8 methods. They are the state-of-the-art neural style transfer methods. They have reasonable generations, but the generations are not very realistic to our human eyes. And this is because the previous style transfer methods only consider the 2 fidelity terms. One is the style fidelity, that is to keep the style information in the style reference image. Another is the content fidelity, that is to preserve the spatial structures in the content image. But in our work, we propose that there should be a 3rd evaluation dimension in addition to the 2 fidelity terms, and we call it zero fidelity. So a generation should achieve a good balance between the 3 fidelity terms. Here I say balance or trade-off. That is because we cannot achieve the best performance for the 3 terms simultaneously. We can only achieve a good balance or trade-off between the 3 fidelity terms. So the problem is, how can we push the generation towards the real distribution? So here we consider this problem in the style space. This is the latent space of a generative model. So we embed the artworks, like many artwork images in the data set. We embed them to the style space. Then if we apply some clustering algorithms to the style space, then we get some clusters of different styles. Then if a generation in the latent space is closer to the clusters or the centroids of the clusters, then it is more realistic to our human eyes because it is closer to the real artwork distribution. So then the problem is, how can we further push the generation towards the centroids of the clusters? Here we use a very well-known machine learning tool called vector quantization. So in this work, so vector quantization is very simple. So we have a generation feature Z, and we search for its nearest neighbor in a pre-constructed codebook. Then we replace the generation feature with the nearest entries in the codebook. And this is vector quantization. It's very simple. And it makes sense because the pre-constructed codebook refers to the clusters. So each entry in the codebook actually refers to each centroid in the above style space. So if we replace the feature with the entries in the codebook, then in fact we push the generation towards the centroids of the artwork distribution. So this is vector quantization, and I want to know that some current day some state-of-the-art image generation models like Stable Diffusion also uses this technique. Like if you are familiar with Stable Diffusion, it has another name called latent diffusion model, and here the latent refers to the vector quantization based feature representation. Then the diffusion means that they apply some diffusion based probabilistic models to the feature space. So but I want to know that they are the motivation of their of that work and this work for using vector quantization are different. In their work, they want to achieve a compact representation using the vector quantization. But in our work, we want to use vector quantization to push the generation towards the real distribution. They are generally similar in mechanism, but different in motivations. And also, I want to know that by using some tricks, we can make the vector quantization be differentiable. So that means that the pre-constructed codebook can be jointly optimized with the whole neural network, the whole neural style transfer framework. So the codebook is actually learnable. It's not manually designed by our humans. So it will be more effective in modeling the artworks. So here we evaluate the vector quantization module on the most common style transfer framework. It is the autoencoder based framework. Here, an encoder encodes the content, that is the photo, and also an encoder encodes the artwork, that is the style image. Then a style transfer module fuses the information from the two encoders. Then a decoder decodes the stylized outputs. And if we apply vector quantization to the outputs of the encoder, then the magic thing happens that so the generation, we have a new generation here, and the image, so most of the artifacts have been removed in the generation compared to the non-vector quantization version. And this is because the vector quantization actually pushes the generation towards the real distribution, real artwork distribution. So if there are not such kinds of artifacts in the real artwork data sets, then it will has a lower probability to present in the generation. So this is the effective vector quantization module for style transfer. And style transfer is a very subjective task. So we often want to perform some user studies to evaluate the performance of methods. But here we design a different user study, and we call it artistic Turing test. We want to evaluate whether the generation is very realistic to our human eyes. So in this user study, we present 20 questions for each user. And in each question, we show two images. One of the image is a real artwork, and another image is the artwork generated by our method according to the style of that real artwork, and also the content from a random photo. So in here, I just show two examples to you, and so could you tell me which one is the real artwork in your opinion? Maybe someone can type in the chat. Oh, left.
Yeah, that's what I left.
Left. Anyone else? Left too. Okay. Thank you. So sorry that you are wrong. So actually, the right one is the real artwork painted in the 17th century, and the left one is our generation according to the photo and the real artwork, the style of the real artwork. And now you have one more chance. Here are two indoor images. So which one is a real artwork in your opinion? You can type in chat. Oh, right. Right. Right too. Okay. Sorry that you are wrong. And the left one is a real artwork, and right one is our generation according to the random photo and the style of the real artwork. So actually, if you want to see more examples, you can scan the QR code here. You will answer 20 questions and you will get your score finally. So
this method, besides this vector quantization, what's the actual method? What is this? It's not a game. What is the method you're using?
I just combined vector quantization with the autoencoder based framework.
Okay.
We want to testify
So
or
it's not, you're not using game like adversary amount or anything.
we use some adversary
Yeah,
loss.
like a game, right?
Yeah.
Basically a game.
Yeah, we use adversary loss. Yeah.
But it's you don't call it a game.
Not a standard game, I think. It's an encoder, autoencoder. Yeah.
Okay, so your new thing is you are doing the vector quantization.
Yes.
Right?
Yes. Yeah, here are the statistical results of the test. We show the artistic Turing set test to 70 different users, and we collect their results. And each user responded to 20 questions. And here here you can see that the average correct response is 10.31. It's just closer to the random guess result. That is 10 out of 20 questions. So it means that the generation is truly realistic to our human eyes by our methods. So we just compare this image to the previous style transfer methods. And you can see that our generation is more realistic, much more realistic compared to them. Although the previous methods can generate reasonable style transfer results, but like the yellow color, some texture details, but our generation is more realistic to our human eyes.
Is the style transfer happening? I don't know why I have a feeling that, like for instance, can you go back for a second to the other picture you were showing with the landscape, with the,
Oh yeah, that one. Oh yeah, that one.
yeah.
This one, yeah.
Not this one, the other landscape, the dark one.
This one?
Yes. Okay, so what was where you were showing your, when you are showing your transfer, it's gonna further down,
Oh yeah,
and the results dash.
this one.
Right. So, okay, so you claim that the top one is better,
Yes.
but it doesn't transfer the style.
Yes, that is the
The style has these little lights. It has the dotted thing even for
yes.
for the pictures and stuff like that.
Yes.
So it's obviously it is transferring. I mean, it's
Yes.
clearly a painted picture.
Yes, you are right. You are right. So as I said before, we just achieve a good balance between the three fidelity terms, the style fidelity, content fidelity, and the visual fidelity. So our method will often preserve fewer style details compared to the previous method because we want to enhance the visual fidelity.
So the visual fidelity you are using the VQA as vector quantization. How are you achieving that?
You mean the evaluation or
No,
the
no, no. Using the
training method? We just use vector quantization. That's all.
you indirectly
Yes.
visual, but that's, I mean, long shot, right? You're just saying if you do the quantization, it will be visual fidelity. But that's, I mean, that's very
So
general.
what's the norm? Like, well, you say that you cannot achieve a you can achieve a trade-off. What do you tweak to? So you have that triangle, right? So it's
Yes,
the
yes.
things that
You're
can
just
do.
using the vector quantization, that's it.
Yeah.
But that's,
Oh yeah. So for the
You can vector
for the trade-off.
1 million.
yeah.
1%.
Yeah.
Very well.
Yeah, for the trade-off, we actually design a interpolation-based framework to trade off between the three fidelity terms. We just do interpolation between the features after quantization and before quantization.
Correlation inside the SD module of the.
In the feature level, like after the vector quantization. Yeah.
Okay.
Yeah.
So before the decoder.
Yeah, before the
I
decode.
mean, he has the encoder, and the decoder. So
Yeah. Yeah.
I mean, the vector quantization, universally used, right?
Yeah.
People use it, and somehow people haven't used in this one. So
Yes.
we use it in
Yes. I think the biggest contribution of this work is we propose the visual fidelity term for style transfer.
That's a problem, right? Because
Yeah.
you can't just say visual fidelity, but actually
Yeah.
you are using
And
vector quantization.
the solution
To
is,
convince people
yeah.
that vector quantization is actually visibility. Most people won't agree with you.
Yeah. So
That's very, you have to have actually term which says that this is actually doing visual perception laws.
yes,
Other laws, right?
yes,
So it's a long shot. I think.
So I think some of the story here is that there are some styles which are easier to apply than others which are not. Like, for instance, if your style it only involves recoloring or enhancement of contours or other stuff like that, that's easier to apply. But applying the style like that, I don't even know why it's that glowing, but clearly other parts, the sky is not glowing the same way like the trees. So
yeah,
what exactly is this?
yes.
What exactly is the?
That's the artifacts.
What exactly? I don't know. Maybe it was the intention of the thing to do that, but
It's a very subjective task. So maybe different people will have different opinions.
Okay, yeah, let's see.
Yeah, here one person asked, so why three fidelity terms cannot be simultaneously improved? So this is a good question. Actually, what I mentioned is we cannot improve the three fidelity terms in one framework. That is, if we have a style transfer model, then we can only achieve a balance between the three fidelity terms. But we can always improve our models. Like we use other models other than autoencoders. We use diffusion-based models or other generative models. Then we can improve the style transfer performance in different aspects. So in this work, I just want to show that vector quantization can be is effective for improving the visual fidelity, and it can be applied to different frameworks, including autoencoder or other generative models. So yeah.
I think as I said, it's universally used, right? Even people are using super resolution diffusion rate.
Yes.
Google and the paper, it's very nice. Yeah, okay, good. So let's continue.
Yeah. All right. So yeah, here. So since the vector quantization is very basic method, then we can generalize our method to more style transfer problems. So in the previous slides, I just showed the photo to artwork transfer, but we can also achieve photo to photo style transfer, artwork to artwork style transfer, and also render photos from artworks. The last task is more challenging because in our experiments, we can only render the landscape images. For more abstract, more complicated paintings, we cannot render them from the artworks. So that would be the future direction. Yes. So the second problem I want to discuss is the content preservation. So here we just surveyed the three benchmark neural style transfer methods, and we find that in the first run, it gives a good stylization result. But if we repeatedly apply the style transfer methods to the generations, then in the 20th round, almost all of the content information has been lost in the generation. That is because in each round, there is a content leak issue. We call it content leak. That means that most of the content, it will lose some content information in each round of stylization. And this is not a significant problem for most of the style transfer settings or applications, but for some specific tasks, it is a significant problem. For example, if we want to render the photos from the stylization results, then this is a problem. And also in some biomedical domain, biomedical image style transfer, if we want to preserve the precise spatial structures or content structures, then the loss of content information is a very severe problem. So to address the content leak issue, we first theoretically analyzed the three main causes of this issue. And the first issue is the autoencoder, that there is always reconstruction error in the autoencoder. And this is the limitation of convolutional neural networks. And the second cause is the bias in the decoder, because a decoder is trained to optimize to output the stylized feature, or stylized image. So it will be biased to styles. And the third cause is the bias in the style transfer module, because the style transfer module is also learned to output the stylized feature. So it will be biased to styles. So here, to address the three causes of content leak, we propose a new framework in addition to the original, which is different from the most commonly used autoencoder-based framework. Here we use the flow-based generation model. And here it is called PFN, it's a projection flow network. And in this network, all the neural network layers are mathematically reversible. It means that it can perfectly reconstruct the inputs from the outputs if we reverse the process, like reverse the neural network layers. So in this framework, in this network, the blue arrows and the red arrows, they extract the information of the content and style image. And here we have the content feature and style feature. And in the testing phase, we use the style transfer module to fuse the features and to get the stylized feature. Then the black arrows reconstruct the stylized output from the stylized feature. And using this framework, all three causes can be addressed because the framework, the network is fully reversible. So there will be zero reconstruction error in the framework. And also there will be zero bias in the decoder because decoder is also reversible. And for the third cause, for the bias in the style transfer module, we proved that some existing style transfer modules are biased and some existing style transfer modules are not biased to the styles. So in our framework, we just adopt those style transfer modules. So then all the three causes can be addressed using this framework. So in experiments, you can see that after the 20-round stylization, our framework flow actually avoids the content leak issue after any rounds compared to the previous methods. And the generation is also good, the good stylization result. And one advantage of this method can be demonstrated in the application of content style separation. So for example, if we want to, we assume that one image is composed of the content and the style. So if we want to separate or disentangle the two terms, then our method can be more effective compared to the previous style transfer benchmarks, including ADAIN and WCT. So you can see that our generation, this is the visualization of the content feature maps. And you can see that it can, our result preserves more content information like the sharper boundaries. And also it can remove more, it can peel off more color information compared to the previous methods. You can see that the WCT, in WCT results, there are a lot of color information. So this is one advantage of our method. So I have discussed the two limitations of current neural style transfer methods, and maybe some of you are curious. So what's the use case of style transfer? Can it only be used for entertainment, like help artists or general public to draw paintings? Can it be used for other areas? So our answer is yes, we can the style transfer can help the machine learning itself. So in this work, we use style transfer to help the neuron cell recognition task. So a neuron cell is generally a 3D tube captured by the electronic microscope. And the neuroscientists want to render the complicated neuron structures from the 3D tube. So as a first step, the 2D recognition is very important. So here is a very famous neuron cell data set called cell pulse. And it is collected by different devices and also different labs. So you can see that the 2D slices are quite different in the shapes and object shape, the cell shapes, the colors, the boundaries, the textures, the illumination information. They are totally different, very different. So it means that we cannot always collect a very complete data set to train our model. So if our model is only trained on a small subset of all the potential domains, then there would be a problem for the out of domain testing samples. So here, if we input the out of domain image to the pre-trained segmentation cell pulse segmentation model, then the ground truth, and then compared to the ground truth, you can see that the results is really bad. It cannot render most of the cells in the original image. But if we transfer the out of domain image to the training domain using the style transfer, then we input the image to the same pre-trained cell pulse model, then the result is much better. Compared to the previous one, you can see that the result here can predict or can present most of the cells in the original image. And this method also works for the other medical domains like the X-ray images. So if we have two X-ray data sets, one is the training data set, another is the testing data set. They are collected by different devices or different hospitals, then they would be different. They would be visually different. So if we input the image from the new data set to the pre-trained model, then it will give some errors. Here you can see that the red areas are the errors, but if we transfer the image to the pre-trained to the pre-trained domain, that is the training domain, then the segmentation would be much better. Segmentation results would be much better compared to the previous one. So this is just one example how style transfer can help machine learning itself. So maybe in the future, there are more, we can explore more directions, more topics in this direction, how to use style transfer to help different biomedical domains or other domains. So I think that's most of the topics in this talk. I have talked about efficient data annotation, I've talked about high quality data creation, and we are curious what's the next for the data aspect AI. So here I just share some of my own thoughts with you. And the first is I think is the foundation model. So here in our previous work that is published on MICAI 22, we collect 11 different X-ray data sets, which are generally the public data sets. So these data sets cover different body parts and different machine learning tasks like single class classification, multi-class classification, object detection, segmentation. They are used for different tasks, but we use those images for training a foundation model using the contrast learning and continued learning. Then we fine-tune the foundation model on different tasks. Then actually, we find that compared to the previous methods, that is the single domain pre-training, like the single domain contrastive learning or single dataset contrastive learning, it performs much better and also better than the training from scratch or pre-training on the ImageNet. So this work inspires that if we can collect more data for a specific domain, then train a model based on the large scale data, then the model would help many downstream downstream tasks in that domain. So in the future, we can explore more directions. Oh, we just used the SimCLR. That is a very famous benchmark contrastive learning method. And the second direction is data-driven knowledge discovery. So currently, I'm working with the medical scientists in Harvard Medical School to see if we can use generative models or deep learning methods to help them discover new knowledge, new medical knowledge. So here is just one of the initial works. So here you can see that here is a very high resolution, extremely high resolution cancer tissue slice. So they are generally 50K by 50K pixels, very high resolution. And in current days, the medical scientists often use clustering-based methods to get different areas of the slice, the whole slice. And there are often some errors. So in this work, we try to apply the clustering algorithms to the latent space of generative model, that is variation autoencoder. Then we get different results compared to the previous one, the previous conventional methods results. And we present this result to the medical scientists, and they told me these results are generally reasonable to their domain knowledge. So it means that actually in this way, we can discover new cancer tissue motifs or knowledge to help the medical scientists. So this is just an ongoing work. And I think in the future, we can explore more interesting topics in this direction. That is how to use deep learning to help knowledge discovery, not just improve the performance of segmentation or detection. And the last one I want to discuss is human AI co-creation. So current days, generative models have shown its strong creativity, like the ChatGPT Stable Diffusion. But I believe whenever now or in the future, the generative models cannot replace the creativity of humans. So I believe in the near future, human AI co-creation would be a very emerging, very hot topic. So under this direction, I have several thinkings of the topics. The first is how to better improve the interactivity or interpretability of or controllability of the models to better help the creativity of humans. And the second topic is to analyze the creation social impact to human society. So we can work with social informatics experts to analyze the social impacts of the highly realistic creations. And there are some issues like the ethics issues or fairness issue. And I think the machine learning experts and the social informatics experts should work together to improve current models. So the third direction is very interesting. It's called co-creation, a new co-creation interface. That is to say our current model like ChatGPT or Stable Diffusion, they use the natural language as the interface between the human and machine. But I believe in the future, maybe we can explore new interfaces, which is also user-friendly. For example, can we let human to create realistic contents in the VR or AR space? And this interface would be so this is a more immersive environment, and this interface would be useful in some specific cases compared to the natural languages. So currently I'm discussing with some HCI experts to explore this direction to see if we can set up some prototypes for this interface. So in summary, I have in this talk I have discussed efficient data annotation with active learning. I have discussed high quality data creation with generative models and some applications to biomedical domains and some future directions. And I have published nearly 30 papers on the good conferences and journals, and some of them have not been covered in this talk. For example, I have some earlier work on image understanding, that is to understand the objects or scenes in the images. Here you can see a very interesting example. We want to infer the future path of the objects. So the person should not crash into the car. So there is a probability for the future paths here. And also for multimodal understanding, I have studied several tasks like image captioning, video captioning, emotion or sentiment analysis. And they are and I think the core problem here is how to fuse the information from different modalities and to meet the requirements of different tasks. And also for effort efficient learning, I have discussed some data efficient learning problems like active learning and semi-supervised learning. But I also have some several work on the effort efficient learning. That is to reduce the human efforts in using the deep learning models. So for example, the neural architecture search task is to discover the neural network architectures from the data set. That is the architecture is fully learnable. It is not manually designed by humans. So this method is useful in some specific cases compared to the manually designed models like ResNet or Transformer. So it will be effective for specific applications. So at the end, I want to thank to my many collaborators. Like when I was in I want to thank to my advisors or managers when I was in Zhejiang University, Harvard, Baidu Research, Carnegie Mellon, Nanyang Technological University, and I also want to thank my students and interns I collaborate with. They are really smart. They are really inspirational, and we have done a lot of interesting work in our collaborations. And I also want to thank to some other collaborators. Without them, I cannot achieve my current accomplishments. So thank you all for listening, and that's all for this talk. And here is the QA section. I welcome any discussions or new ideas. So thank you.
So we are a bit over time. So if somebody wants to ask questions, please ask questions which can be answered quickly.
Yeah, some quick questions. Yeah.
All right. Cool. Okay. Well, thank you very much for your presentation. It was very interesting. Thank you for people, family, and Zoom who attended.
Thank you again for listening. Thank you.